So, as per last week, I'm going to hand over to Alex here because he's been reading through the GDC Vault.
Yes,
checking out the latest presentations that were made at GDC 2024. And this week, Alex, you're going to be talking about path tracing, right? So, what are the games you're talking about first of all?
Well, I guess I will start off with that GDC presentation here, because I had looked at GDC and technically GTC, which always seems to happen around the time of GDC as well. And that's the NVIDIA's graphics technology conference, which, like the games one, covers a variety of topics, and just only a handful of them are actually about real-time rendering, because NVIDIA is a huge company, you know? Yep. So let's talk about that GDC presentation. This one was actually a generalized presentation by Adam Mars, who's a great guy. He actually sent me GPU Gems, not GPU Gems 2, Ray Tracing Gems 2 in a analog book form. It's huge. Very cool. And Evan Hart. And they're talking about just generalized about real-time path tracing for game engines. And they did it, actually, they talked about it in a pretty NVIDIA non-specific way, because I think they're trying to argue that this is the future, regardless of GPU manufacturer. And I think Intel would agree with them. And in that presentation, they did focus in on, though, the UE5 branch that they're working on as like a case study about how they're bringing path tracing to games. They talked about a lot of things that I've talked about on the channel before and that we've kind of discussed regarding path tracing in games. Like, for example, in the UE5 branch that NVIDIA is working on, that you can download for yourself if you're a developer, this 5.3 branch, they've replaced like the way lighting is done for direct lighting to use Reister direct illumination, which is NVIDIA branded as RTX DI, but it's a generalized technique. It works on all hardware. And that is just like a really specific way to like sample lights in a clever way, so you can get ray trace shadows from every light source in the game. And that's a big difference, obviously, than in the past, where you have to like run shadow maps or like explicit ray tracing for each light, and that's very expensive. So this is like one way to get like one aspect of the rendering pipeline done with ray tracing. But that wasn't actually the most interesting thing in the talk. We've talked about that before on the channel before. What I thought was interesting is how they mentioned UE5's big push was Nanite, obviously, and Lumen. And for them, they actually see Lumen as a good system. And they don't want to, if people are going to be using this UE5 branch that they're making, which is what they want, they don't want people to have to get an entirely different lighting system in their game. So for that, they decided to use UE5 Lumen for this NVIDIA branch, but just do extensions of it. For example, UE5 Lumen, at its basis for the diffuse lighting, uses the surface cache, which John has talked about in his videos before. I have as well too. And, you know, it's a way to get really good performance on things like consoles, obviously, but it leaves like a lot of quality there up for grabs. It's not particularly good at things like emissive lighting, for example. So like little lumen strips in the environment, glowing lava, windows at night on buildings, you know, like those are usually done with like glowing textures in games. And Lumen isn't very good at approximating the lighting from them. It usually has like no light, or all that light's in screen space, or it's flickering light. So they extended Lumen essentially to actually use Reister GI. So it actually explicitly is going to be sampling emissive lighting. And they had a really cool demo video that they showed that off and all that working. Another thing that they talked about was how they use Lumen hit lighting for reflections. Now, this is once again something that the base engine actually supports, but a lot of games don't ship with it at all. It's not using the surface cache for lighting these objects in reflections, but is actually going to explicitly sample them. And the thing that they do differently than the base UE5 engine is that you can also use SER with it. And SER is a technology I've talked about before on the channel. I think I talked about it last week. A shader execution reordering, where the Ada Lovelace GPUs of the RTX 4000 series have like their own ray tracing API. And it's way better at doing a kind of like really disparate shading that is done for path tracing. It's way better at that. It makes it so that the GPU is more fully used instead of being mostly idle when doing path tracing. And their branch of UE5 does that for the reflections in the game. So it gets better quality and way better performance than the base UE5 version, which is kind of cool. And I'm hoping that developers do take a look at using this branch in the future for PC ports. And I'm pretty sure we should expect, for example, like CD Projekt Red to be using this, as well as a couple other studios. I'm pretty sure Black Myth Wukong is going to be using this version of the engine based upon the press release. But I was pretty excited about that. And also the one thing they mentioned is that Epic has taken things from this branch in the past and put them in the base engine. And I'm hoping that happens as well too. There's kind of rumblings about certain aspects of Lumen being changed in the future regarding these things so that they better support hardware ray tracing on PC. And I'm hoping that they take some cues from this. One thing that the presentation did not talk about, is one thing I'm very curious about, is how hardware path tracing like this fits into Nanite. Nanite's very interesting, is where it's constantly adjusting the amount of geometry on screen based upon how many pixels there are and how close you are to an object. So it's always changing. Like every frame could have a different, if a camera in a game is, for example, like breathing animation, the amount of triangles in each single frame could be different, even on a static camera. And that doesn't fit too well into any software or hardware ray tracing paradigm, because usually these things have like static LODs or static things that are loaded into memory. And they didn't talk about that, unfortunately, in the presentation, which made me hungry for more, for more info that they didn't talk about, because it's actually just like a generic problem in general. How will Nanite fit into the future of hardware ray tracing? Right now, if you run a game with hardware ray tracing and it has Nanite, which pretty much all of them will do, Epic and UE5 have made it so that there's a fallback mesh that is defined by the creator of the game. And it's usually like a lower resolution version of that mesh, which is static. It doesn't change. And that kind of works for really diffuse illumination and some reflections. But for things like shadows, it doesn't work at all, really. So I'm very curious as to what the future of that is. They didn't talk about it in the presentation. Maybe we'll see more about it with their Blackwell GPUs, or future versions of UE5. But I was hungry for more information after this presentation, to say the least. But it was good. It was good.
There's no payoff on that, though, is there? You're still hungry.
I'm still hungry. I'm no payoff.
You're ravenous.
Ravenous hunger for
days on
for more information. Okay, so
there's a lot going on with Unreal Engine, isn't there? I mean, there's the 5.4 update, which is seemingly a lot faster. It's interesting because there's been a lot of you could say misconceptions about Unreal Engine 5. Simply because it's running on older versions of the engine that are less performant than the current one.
Yeah, really.
So it's going to evolve just like any other technology. So we're interesting.
Talking about like Lords of the Fallen now, like I'm gonna joke on them a bit and say like you really shouldn't have massive stutters in your game during combat, but they're not the only ones responsible for that. Epic is too. These systems that they make don't scale.
I played
so well.
Fortnite the other day, Lumen Nanite, and the first couple of playthroughs are still really, really quite poor.
Yeah, geez,
you have to play the game a couple of times to actually seemingly cache the shaders.
That's not good, man. So we'll see where that goes in the future. I'm gonna hopefully be now working on a UE 5.4 vid in the future very soon, now that it's working right. So I'll hopefully talk about that. But anyway,
maybe worth a look at Immortals as well in that breath,
Yeah, maybe we'll see. Then that's that presentation, which was a GDC presentation, and it was very good. There was also 2 GTC presentations I was very curious about. The first one was Alan Wake 2, a deep dive into path tracing. By Kia Kandar and Yua Seolholm, a person from NVIDIA was Yua there, and Kia was from Remedy. And this presentation was going into the path tracing implementation of Alan Wake 2. And I thought this was interesting. It wasn't a lot of new information necessarily, but it was a great contrast to what I talked about last week with Avatar. Avatar was all about getting really high performance on console, making a lot of cuts and corners here to do that, and it fits the art style of the game. For Alan Wake 2, it's such a precise game, and path tracing is such a precise technology. You need like pixel perfect shadows. You need pixel perfect lighting for it to actually coalesce into an image. That cannot work at all with any of the optimization strategies that were done for Avatar. For example, in Avatar, I talked about last week, the BVH structure, the objects in it are very low LOD. They're very low level quality. They have like averaged materials on them. They're like really, if you were to see them, you'd think it looks like a game from like 2003. If you did that with path tracing, the lighting would not at all line up. The shadows would not at all line up with like the primary stuff you're seeing in the primary view, and it would look awful. It wouldn't work at all. So they had to have essentially everything in Alan Wake 2's BVH structure, this thing that is running on the GPU. They had to have it be just the same high quality as the primary rendered graphics. And that is a huge ask in a game like Alan Wake 2, specifically in like those sections where you're playing a saga, where there's a lot of moving vegetation, interactive vegetation, little tiny blades of grass, all these little things. So for them, their optimization strategy was different. They're like, we need to have every little bit of perfectly moving geometry in our BVH structure. Okay, so how does it run in real time? What they do is they have like, here's an image on screen, like 10 meters in front of the camera. It's running at full rate. So that's actually pretty rare for a lot of ray tracing games. Even like if you go to Spider-Man on consoles, like Spider-Man 2 on consoles, all the stuff in their BVH is running at like half rate or lower. So if you like were to look actually at Spider-Man running inside of a perfect mirror reflection, he'd only be running at 30 FPS in the 60 hertz mode. So they have to do that. They have to have this 10 meter area in front of Alan in Alan Wake 2 or Saga in Alan Wake 2 runs at full rate, like 60 FPS or higher. But everything beyond that, it starts to animation degrade. So it's like half rate after 10 meters. And then after like 30 meters, it's like third rate. And then it goes even to quarter rate. So this is like the age old way to get things running better in the distance is to just reduce how often they're updated. And we've seen that, you know, I always talk about Dark Souls doing this, but having it done for ray tracing is really sensible. And usually at a distance, you cannot tell because, well, they're far away and they're small pixels anyway. And it's only the lighting that is technically not running at full speed. But I find that an excellent kind of, I don't know, optimization tip to try and get path tracing in modern games until, you know, future hardware somehow changes that. Another thing that I thought was cool in the presentation is we knew about this and it explains a lot about why the game looks the way it does is the game, and I talked about it in my review, they're still using some of that baked lighting in the game, even if you have path tracing on. And they explain exactly what and how and why that is. And it's essentially, they do, with the path tracing on, 3 bounces of light, both diffuse and specular actually, which is pretty intense. So it's like way higher than the amount in Cyberpunk or most other games. And after that, after those 3 bounces, it does a ray traced ambient occlusion check. And it says basically, is this thing obscured by another close by object? And that, with that, they're explicitly sampling the baked GI underneath for the last bounce. So sometimes, what this means is sometimes in some scenes, you won't see anything of that baked lighting because it's all just like the real path trace lighting being done there. But for certain scenes, depending upon how they've been authored, some of that baked lighting will then show through because that after that third bounce, it's being sampled explicitly. And I thought that was interesting because it solves a certain problem with that game where They don't want the lighting to look too different with path tracing at times because it's a very artist-driven game, but also the game doesn't have any sort of caching structure for its lighting. It usually, like if you were to path trace an image, you wouldn't want to just have like 3 bounces, ideally, or even 4. You'd want to have infinite amount of bounces to capture all the light that the real world has. Well, that's impractical. So usually games come up with some sort of caching structure, like Lumen does, for example. And here they didn't have one, so their caching structure was actually baked lighting. The game doesn't have a moving time of day. It actually makes quite a lot of sense. I may be a little bit annoyed with sometimes the inaccuracies it brings into the image as a result, but it works for Alan Wake 2 more or less. And I thought that was interesting. Okay, last presentation that I saw. That was pretty cool. And this one is RT Overdrive in Cyberpunk 2077 Ultimate Edition, pushing path tracing one step further. This is with Jakub Knapik, who I talked with when we did the look at DLSS ray reconstruction, the little panel we had here on DF.
It was the roundtable.
The roundtable panel. That was really cool. Michael Murphy and Pavel Kozlovsky. And this is a lot of retreaded information actually from stuff that we talked about during that roundtable discussion. Also, I've talked about in my videos before, but there were 2 things that I didn't talk about then because they weren't really known. One is that originally, the original version that shipped of RT Overdrive, that like beta version, was actually not using Restor GI like I assumed it was. It was just using pure path tracing. So that means, well, Restor is a form of path tracing. It's just way better at it. It's just more accurate for the amount of samples. But the point is, the original version that John like covered in like March of like last year was using like rays that were sent out in a rather random way to get indirect lighting. And that means it was that the denoisers at that time were having to do a lot of heavy lifting to get any image at all out of that. So they switched over for the 2.0 release, I believe. They switched over to Restor GI for the indirect lighting, and that made the image coalesce even better than it did before. So they had to, it spends a little bit more, milliseconds frame time to do that, but you get a way better image, so the denoiser has to do less work. But the most important part of this presentation that we didn't know about beforehand was how the Ultimate Edition version of Cyberpunk 2077's RT Overdrive actually shipped with a Radiance cache, this caching structure I just talked about earlier with Alan Wake, or what Lumen also has. Lumen uses the surface cache thing to kind of store lighting information in it and does other like multiple bounces from it to get like more lighting in the environment over time. The original version of Cyberpunk RT's Overdrive didn't do this, so it would just terminate after 2 bounces. And that is actually enough for plausible lighting, but it can technically leave some like more complex overlapping geometries as being a little bit overly dark. And also, it's not necessarily the best way to save performance because you're having to do a lot of real path traced lighting at that point instead of just reading from a cache. So it's more expensive. So for the 2.0 update here, this Ultimate Edition, they implemented a new NVIDIA technology called SHRC. It kind of looks like Shark, and they have a little logo for it that looks like Shark. And it's spatially hashed radiance caching or cache. And this is different because it's like all the diffuse, like hard edged geometry of the world. There's like this little structure on its surface, and they store the information essentially from the path tracing into it for those for that diffuse lighting. And this upgrades the game both visually and technically performance wise, because now there's a max of, I think, 4 diffuse bounces. The reason why they keep it to 4, which is a reasonable number, is because the more amount of bounces that are cached in one of these surface caches or structures that are just running on top of the path tracing, is the more that are bounced and cached there, the larger the latency is between lighting updates. if you think about it, so you could turn off a light in a room and it could take like multiple frames for that light to actually turn off. It'd be a little awkward looking, as you can imagine. So they limit it to just 4. So it's going to make areas of the game that were a little bit implausibly darker actually much more realistic looking. Another thing that it does is that they have to technically do less real bounces all the time. So they can turn that down a little bit, instead relying a little bit more on the cache, which should technically help performance. I thought this was cool because now NVIDIA kind of has multiple technologies to implement path tracing in games. And this Radiance cache that they developed is a vendor agnostic thing. It works on all GPUs. So it won't be NVIDIA specific. And I think that's great because it's going to allow for more path tracing implementations in games. And it answers a good question of like, okay, what do we do like to save performance? And what do we do to have like really plausible lighting? And that was it. So 3 presentations. I liked them all.
Well, Alex, I heard that NVIDIA are all in on AI now. Don't care about gaming anymore.
They don't care about gaming. They don't care about path tracing anymore. It's all AI. No, in fact, the SHRC, Shark, the spatially hashed whatever, it is a competitor technology to another technology that NVIDIA has made, which is NRC, Neural Radiance Caching, which is a machine learning based illumination caching for path traced games, which uses AI. They produced a version of now they call it RTX GI 2.0, but you can download it from a GitHub. And it's basically some of the stuff they showed off in this presentation, but you can show the difference between this new spatially hashed radiance caching technique and what NRC does, which is a machine learning one. And you can see them in real time. So maybe some games will implement that, but I actually kind of almost doubt it because it's very NVIDIA specific. Maybe it could be like an ultra high end option on like a CD Projekt Red game in like the future. But right now, I think most people, if they're going to do path tracing, they're going to use this vendor agnostic solution for sure.
Good stuff. I don't know how to cap that off.
Sorry.
No, me neither.
I talked a lot.
Don't need to see the presentations now. I've heard it all.
Oh my God. The presentations are way larger than what I said.
Oh, I bet. I bet. That was amazing, Alex. Really, really great breakdown.
Oh, thanks, mate.